I welcome you all to the session of engine system and performance, and today we shall discuss about turbochargers. In the last class we have discussed about superchargers, and we have seen that superchargers are used to increase the pressure of intake air, and the increase in pressure will essentially increase the density of the incoming air, and objective is to enhance the mass of air to be drawn into the engine cylinder during intake stroke. There are several avenues to increase the mass of air to be drawn into the engine cylinder, but we have discussed increasing the engine speed is also associated with frictional losses. Then increasing the cylinder volume is not again a viable option. So, the only option which is there to increase the density of intake air so as to increase the mass of air to be drawn into the engine cylinder, and if we increase the mass of air during intake stroke to be consumed by the cylinder, then certainly greater amount of fuel can be burnt and power output from the engine can be increased or enhanced. So, in this context today we shall discuss about turbocharger. Let us first discuss what is this and in which aspect this is different from supercharger. So, the concept of turbocharger was first proposed by Dr. Alfred J. Bucci in 1915, who developed this unit for a diesel engine. So, let me write here the first concept of turbocharger was proposed by Dr. Alfred J. Bucci, and that is in the year of 1915. He developed this unit turbocharger for a diesel engine. Now, so this is the unit. In a turbocharger, the entire unit or assembly is known as turbocharger. In this unit, a small turbine is there, and that turbine is rotated by the exhaust gases of the engine, and the turbine is connected via a common axle to a compressor to increase the power output of the engine essentially by compressing the air above the inlet conditions. So, compressor is there to increase the density of the air above the inlet pressure and inlet conditions, and to run the compressor there is a small turbine which is again rotated by employing or exploiting the kinetic energy of the exhaust gases. Now, what we have learned in the context of supercharger is that superchargers are again nothing but compressing the air to be drawn into the engine cylinder by using a compressor. Now, the compressor is rotated or compressor is driven by taking certain amount of energy from the engine shaft. So, if we need to borrow some energy to run the compressor from the engine itself or engine output power itself, then certainly we need to compromise with the engine efficiency. Instead, what we can do here, the turbocharger is essentially having one small turbine, and that is rotated by the use of exhaust gases. So, this particular turbocharger unit has a few advantages. What are those? It is small in size and it can be operated for larger flow rates. So, advantage if we write here, so just we are talking about introduction of the turbocharger. So, advantage number 1 is small in size and used for larger flow rates. Number 2 is, if we talk about that turbocharger in a sense brings economy, rather fuel economy, by how? So, it has also the capacity to reduce fuel consumption due to the fact that the energy which will otherwise will be lost into the ambience with the exhaust gases can be used by the by the turbine, or rather by rotating a turbine. So, if we look at precisely, then we can see turbine or turbocharger essentially brings fuel economy due to the fact that certain portion of energy which will otherwise will be lost with the exhaust gases can be recovered. So, we have studied in our internal combustion engine course that exhaust gases carry some enthalpy. Now, that enthalpy will be lost if we do not use it properly. If we use that enthalpy to rotate a turbine, perhaps we can recover certain energy which will otherwise will be lost. So, that way this has some advantage that brings fuel economy due to the fact that certain amount of energy with the exhaust gas stream is recovered. So, these are the advantages, but having discussed all these advantages, there is still a disadvantage. What is that? That disadvantage is using turbocharger, it would be very difficult to produce higher pressure ratios. Rather, the sole objective is to increase the pressure of the incoming or intake air. Now, using this turbocharger, it is not possible to increase the pressure ratio when the engine speed is low. That means, if the engine speed is low, certainly energy available with the exhaust gas is minimum, and hence turbine cannot be rotated with high speed, because as I said turbine is rotated only due to the kinetic energy of, rather it is rotated exploiting the kinetic energy of the exhaust gases. So, this is a disadvantage. So, if I write here disadvantage, then just disadvantage, that number 1 is unable to produce high pressure at low engine speed. I have already explained why it is so. That means, we really cannot boost pressure ratio, or we cannot have a higher pressure ratio when the engine speed is low, because when engine speed is low, the exhaust gas that is expelled from the engine is having less energy as well. So, these are the this is the disadvantage. Now, let us look into the hardware of this particular unit. Let us first discuss about what are the components there with this unit, and then briefly its application. So, if we look at, we can see that this is the entire turbocharger unit. In this there are 3 components. So, if I write first, the first component is number 1 is a compressor, like what we have seen in the context of supercharger. This compressor is dynamic, typically centrifugal compressor is used, and this compressor is mounted or incorporated with the you know intake manifold of the engine. Then 2 is a small turbine that you can see. So, if we look at the upper part of this unit is turbine. So, this is the turbine. I will explain the operational process of this particular unit. A small turbine is attached to the exhaust manifold of the engine. So, you can see this, the lower part of this unit is the compressor, and that compressor that you can see from the arrow, this is essentially ambient air which is drawn into this compressor. That air is compressed by rotating the runner of the compressor or rotor of the compressor, to be precise rotor. So, the rotor of the compressor is used to rotate to compress the air, and in this direction compressed air is coming out, which is again fed into the intake manifold and it eventually drawn into the engine cylinder. Now, this compressor is connected to this turbine, so we have a common spindle. So, that is the common shaft, to be precise, common shaft. So, in this common shaft both compressor and turbine, these two units are mounted, and the upper part of this unit is the turbine, you can see. So, turbine, if you look at, this is the turbine engine exhaust gases. So, exhaust gases that is expelled from the engine cylinder is allowed to go into this turbine, and that gas or gases have high enthalpy kinetic energy that is used to rotate the turbine wheel, and eventually doing some work, that gas eventually or gases come out and leaves through this pathway. So, as the turbine is rotating, because of this movement of the exhaust gases, since these two units are mounted on this common spindle, so the compressor will be rotating, and by virtue of this rotation the air which is drawn into from the ambience can be pressurized, and that is what the objective is. So, just here I would like to write, there is a common spindle, a common spindle is used to mount both compressor and turbine, and the spindle is supported by a fully that is a pair of fully floating bearing. So, plain bearing rather. So, the common spindle, if I write just one line over here, this common spindle, so this is supported by a pair of fully floated plain bearing. Okay. So, essentially you can understand bearing that you have studied in our machine design course. Bearing or bearings are machine element, and these elements bear some load, static as well as dynamic. So, the common spindle is supported by a pair of fully floated plain bearing and bearings rather, and this common spindle houses both compressor and turbine, and by rotating the turbine we can rotate compressor. So, this is all about the hardware of this turbocharger. Now, let us talk about the mechanism. So, if we talk about this compressor or dynamic compressor, this compressor has two parts. One is rotor, that is rotating element, another one is diffuser. So, these two parts are important to increase the pressure of the air as it moves along them. So, the dynamic compressor has two components or two parts. One is the rotating element, that is rotor, and another one is diffuser. So, these two components are responsible to raise the pressure as the air moves along them. So, this is the compressor, and we have studied about turbines, perhaps you studied steam turbine, gas turbine. So, this is also a gas turbine, but the size is very small, right. So, this particular unit turbocharger is used in marine diesel engine. Rather, application of turbocharger spans from marine diesel engine. So, if I go to write applications of turbocharger. So, the applications span from marine diesel engine to vehicle diesel engine. Sometimes also used in boosted SI engines. So, sometimes if we need to increase pressure ratio of the SI engine, that is boosted pressure SI engines, turbochargers are used. So, these are the application. I forgot to mention one important element. See, compressed air that comes out from this compressor is not directly taken to the engine or rather intake manifold. Sometimes depending on the requirement, and in particular if this unit is used for the SI engines, we need to have one aftercooler or intercooler. The sole purpose of this particular unit is to take off certain amount of heat from the compressed air. You know that as the air is getting compressed inside the compressor, its pressure will increase, but with the increase in pressure, thermodynamic consideration will be there, that is temperature also will increase. So, the rise in temperature, if it is beyond certain limit, essentially that in the intake manifold, again the consumed air should be compressed during compression stroke. So, an increase in temperature associated with increase in pressure inside the compressor will be further enhanced inside this engine cylinder, and that increase in temperature will eventually invite one important or rather detrimental problem is which is knock. That is, knock is really a severe detrimental problem for the SI engines. So, for the SI engines, if we use turbocharger, before this compressed air enters into the intake manifold, one intercooler or aftercooler will be there essentially to take up certain amount of heat from the compressed air itself or compressed air stream. Mind it, this intercooler may not be required for the CI engines because knock is not a serious problem for the CI engines. Okay. So, these are the applications, and what I can tell you that for a typical internal combustion engines, rather for the flow rates and pressure ratios of a typical internal combustion engine, the speed of the turbocharger can go up to 10 power 6 RPM. So, just I am writing for the sake of completeness for a typical IC engine. IC engines flow rate and pressure ratio, right, because Flow rate here refers to the flow rate of the charge, essentially that is the flow rate of exhaust gases, and pressure ratio. The speed of turbocharger, try to understand here, speed of turbocharger refers to speed of the turbine, which in turn is equal to speed of the compressor as well, because these two things or these two rotating elements or machinery, rotating machinery are mounted on a common spindle or common shaft. So, the speed of turbocharger of the order of even 10 power 6 rpm is not uncommon, rather it is common. So, this is what is very important. Now, let us talk about one important thing, that is we have discussed about turbochargers, then we have talked about description of turbocharger. So, let us talk about one detrimental aspect or detrimental effect associated with the operation of turbocharger. So, if I write here problematic issue with the operation of turbocharger. So, this is known as turbo lag. So, what is turbo lag? So, this is the questions. So, the phenomenon of turbo lag in turbochargers we need to know. We have discussed about compressor, small turbine though. So, any mechanical component we have discussed in this course as well, electronic control unit. In earlier engines, control of exhaust and inlet valves typically was monitored, or controlling of the operation of inlet and exhaust valve was monitored using a cam and follower mechanism. So, again cam follower mechanism or cam and follower, all these are mechanical components. Any mechanical component we discuss or we consider, it has certain inertia, right. So, no matter how light or how precise you do, there is some inertia associated with the rotating mass. Similarly, in the context of this unit, that is turbocharger, when engine is accelerated, right. So, if engine is accelerated, certainly you can understand engine speed will increase. If that is the case, then the exhaust gas flow will increase. We have discussed today that turbine is rotated solely by the kinetic energy of the gas or gases that is expelled from the engine cylinder. Now, with the sudden acceleration of the engine, engine speed will increase, exhaust gas velocity will increase, but there is a delay of delivering energy that should be discharged into the turbine housing to speed up the wheel. Let me tell you once again, though the engine speed is increasing, the mass flow rate of exhaust gas will increase, still there will be a delay to supply that exhaust energy, the excess energy to be delivered or to be discharged into the turbine housing to rotate the wheel. So, momentarily maybe exhaust gas speed will increase, but momentarily turbine wheel will not be able to speed up. So, there is a delay, and that delay is essentially associated with the inertia of the rotating mass or inertia of the wheel. Okay. So, this delay is known as the transitional period. So, there is a transition between the increase in the kinetic energy of the exhaust gases and the corresponding increase of the speed of the wheel of the turbine. So, this delay which is known as turbo lag. So, let me write here a few lines what is turbo lag. As I told you that if this is the question, then let me write the answer, is when the throttle valve is opened quickly. That means we need to accelerate the engine. If it is opened quickly, the turbocharger essentially to accelerate, this comma will not be there, essentially to accelerate the engine speed, or engine or rather automobile, the turbocharger will not respond as quickly as supercharger does. Okay. So, as a supercharger does. So, basically I have already explained that if we need to accelerate the engine, certainly kinetic energy of the exhaust gases will increase, but the increase in kinetic energy should be discharged into the turbine wheel, and then turbine wheel will be able to rotate in line with the increase in kinetic energy of the exhaust gas. Even though there will be certain delay to deliver the excess energy to the turbine housing to speed up the wheel, and this delay or transitional delay is known as turbo lag in the context of turbocharger operation. So, this is important. So, what I am telling that this transitional response time. So, number 2 is during this transition period, a very little improvement in the cylinder filling process will be there. So, this line what we have written, if I mark it or if I keep it here inside the box, then this line has some significance. So, that means as the engine speed is, or if the driver is accelerating the engine, we need to supply high pressure or greater mass of air to be drawn into the the engine cylinder. Only then we can burn larger amount of fuel and the sudden acceleration would be justified. But if we need to supply greater mass of air, then the compressor will run in line with the requirement of the engine. If we need to run compressor which is connected to the turbine will be able to run at a high speed. So, but the turbine is not responding as quickly as supercharger, that is, if the compressor is connected to the shaft of the engine itself, in that case compressor will be able to supply required amount of air needed or as needed by the engine. So, this is very important. And if we go to the next slide, this transitional response time. So, this transitional response time is known as turbo lag, So, of the turbocharger. Certainly, from the discussion we had until now, you can understand this undesirable phenomenon. So, this is not desirable at all. So, this undesirable phenomenon is associated with the inertia or rotating inertia or polar moment of inertia of the wheel of the turbine or other rotating mass. So, if I write here, this is So, this undesirable phenomenon is associated with the rotating inertia or polar moment of inertia, polar moment of inertia of the rotating mass or part of the turbine. So, that you have studied in your machine design or dynamics of machinery course, that what is polar moment of inertia, rotating inertia. So, this polar moment of inertia, rotating inertia, if I write here this polar moment of inertia can be written, you know, that is written I equal to m into k square, where m is the mass of the rotating element and k is the radius of gyration. So, the turbine wheel is having certain mass, that is the mass of the rotating element or rotating part, and k is the radius of gyration. What is the radius of gyration? So, that is the distance from the axis of rotation to a point where all mass of the rotating element or rotating body is assumed to be concentrated. So, that you have studied in your dynamics of machinery course. So, let me write here this what is k. So, radius of gyration, that is the distance from the axis of rotation to a point where all mass of the rotating element is assumed to be concentrated. Now, question is, knowing the polar moment of inertia I, we can now write the torque. So, torque required. So, then we can write here again. So, torque required to rotate. So, if we are talking about that is the polar moment of inertia of the turbine wheel, then the torque required to rotate the wheel, here or rotating element in a generalized form, that T should be equal to I into alpha, right, where I is the, so this is torque and this alpha is the angular acceleration. Okay. Now, you know that I that already we have discussed, that is polar moment or rotating inertia. So, if it is case, then from this simple equation number 1, we can see that this angular acceleration, that is what we need in line with the sudden acceleration of the engine speed or engine or automobile, we need to rotate the wheel. So, the angular acceleration is inversely proportional to the polar moment of inertia. So, just having the polar moment of inertia, we can double the angular acceleration, right. So, the one way of alleviating or circumventing the problem associated with turbo lag could be to use a light ceramic material for the wheel of the turbine. Let me tell you once again, from the equation itself I can understand that angular acceleration, which is very important for the wheel. So, if we see this angular acceleration for a given amount of torque, if torque is fixed, so then just if I half the polar moment of inertia, we can just double the angular acceleration for the given torque, right. So, if we use lightweight ceramic material for the construction of the turbine wheel, perhaps polar moment of inertia, rotating inertia can be reduced, which in turn will ensure little improvisation of the turbine wheel in the context of turbo lag. Okay. But the question is, whenever someone will be considering lightweight ceramic material for the construction or for the fabrication of turbine runner, he or she must be thinking about the material such that the material will be able to withstand even at high pressure and high temperature, because exhaust gases carry enthalpy, it has some pressure and high pressure, high temperature. So, the material will be able to withstand that particular thermodynamical condition without any mechanical failure. So, this is what is. So, in this context, let me write here one important point to significantly reduce that the turbo lag purely from the perspective of better operation. Of turbocharger, there could be two avenues. First one is to reduce polar moment of inertia, that is use lightweight material, or other avenue could be to use variable geometry turbine, and this is called VGT. So, either we can use lightweight ceramic material to reduce the polar moment of inertia, or else we can use variable geometry turbine or VGT purely from the perspective of better operation of the turbocharger. Now, turbochargers rather. So, if we for this particular case, as I said you that someone should consider the thermodynamical aspects like high pressure, high temperature conditions of the material. But if we look at the second one, that is also really a viable option. So, let us talk about this particular variable geometry turbines. So, if we use variable geometry turbines, okay, we shall discuss about this part later of this class, but let us talk about the turbines used in turbocharger. So, here if I write turbine used in turbocharger are categorized into two subclasses. One is fixed geometry turbines, which are known as FGT, and number 2 is variable geometry turbines, and this is VGT. So, if we consider this particular case first, so we should know why the fixed type or fixed geometry turbines are not suitable for turbochargers, then only we can discuss about this one. So, if we talk about FGT, that is fixed geometry turbines. So, from the name itself you can understand, in this particular case the geometry of the compressor and turbine is fixed, right. So, the compressor geometry and turbine geometry, these two geometries are fixed for this case. So, if I write here geometry of the compressor, or I should write of the compressor plus geometry of the turbine, fixed. So, fixed. So, geometry of the compressor plus geometry of the turbine. So, two these geometries are fixed, and if the geometries are fixed, then for this particular case the boost pressure, that is rise in pressure, is solely determined by the exhaust flow gas, right, the rate of exhaust gas flow. So, here I can write that boost pressure is determined by the exhaust flow. So, if we need to boost the pressure for a wide speed range of the engine, right, because engine can be throttled fully, engine can be throttled partially depending on the requirement. So, if we need to have if we use turbocharger with fixed geometry turbine, which is essentially used to boost pressure solely by the exhaust flow, right, solely by the exhaust flow, then to boost the pressure ratio for a wide range of speed, the turbochargers need to be operated at a large speed, large pressure ratio for the range of flow rates, right. So, and not only that, so let me tell you once again, if we use turbocharger which is equipped with fixed geometry turbine, and we have seen that the fixed geometry turbine boost pressure is solely determined by the exhaust flow. So, that means if we need to boost pressure of the engine, so I mean if we need to boost off, or if we need to boost the pressure of the incoming air for a wide range of engine speed, turbochargers need to be operated at high speed and high pressure ratios for the range of exhaust flow rates. Not only that, when the turbochargers are operated with or at high speed and high pressure ratios, typically turbochargers are required to be protected from two again detrimental effects, and these two effects are known as overspeeding and overheating. So, if I write here again just for the sake of completeness, that so fixed geometry turbine, if we use to boost high pressure over load of for a wide speed range, then enter turbocharger. Turbochargers need to be operated at high speed, certainly rotational, then at high pressure ratios, over a wide flow range. Of the exhaust gases, and if that is the case, this aspect, if I write here, demands that turbochargers turbochargers has to be protected from two detrimental effects. And if we go to the next slide, two detrimental effects are: number 1, overspeeding, and number 2, overheating. Okay, overspeeding and overheating. So, overspeeding and overspeeding. So, these two are very important. We shall discuss about what these two detrimental effects are. Now, the question is, what is overspeeding? So, overspeeding so you can understand when turbine and compressor, these two components are rotating at high speed, right. So, essentially to boost the pressure, that high rotational speed, rather components of these two elements, when they are rotating at high speed and when these components are in touch with high pressure, high temperature exhaust gas, in particular turbine. So, I am talking about turbine because this is the fixed geometry turbine. So, when turbine runner is rotating at high speed to boost the pressure, and when the turbine blades are in touch with high pressure, high temperature exhaust gas or exhaust gases, that particular condition may destroy revolving components of the turbocharger or turbine. So, this is detrimental and this is known as overspeeding. So, overspeeding is when turbine wheel is rotating at high speed and turbine runner is exposed to high temperature exhaust gas or gases, the prevailing situation can destroy revolving components, right. So, this is the overspeeding effect. So, this is not only turbine, compressor can also encounter such problem, issues. So, if you go to discuss about overheating, then overheating, what is overheating? That we have discussed that when pressure of the intake air is high, and that is what we need, because we need to increase the pressure of the intake air, which in turn will increase density and certainly mass of the intake air can be increased. When pressure of the intake air is high, this high pressure air will be drawn into the engine cylinder, and in subsequent stages, so the consumed air will be again compressed further during compression stroke of the engine. So, what will happen? The pressure of the air will increase further in the cylinder, engine cylinder to be precise, right, during compression stroke. Right. So, this rise in pressure will be again associated with the rise in temperature, right. So, that situation, so rise in pressure will be increasing the temperature as well. And this rise in temperature over a duration of time may become detrimental and destroy several components of the engine, right. So, let me tell you one thing, when pressure of the intake air is high, that high pressure intake air will be drawn into the engine cylinder. In subsequent subsequent stroke, that is compression stroke, its pressure will increase further, which will be accompanied by a rise in temperature as well, and that temperature may become vulnerable for the complete failure of several parts of the engine, and this phenomenon is known as overheating. So, this will destroy several parts of the engine, several parts or components of the engine. So, this is known as overheating. So, what you can understand, that if we use fixed geometry turbine, where geometry of compressor and geometry of turbine is fixed, and the pressure or boost pressure is solely determined by the exhaust gas, we have encountered these two different aspects, that is overheating and overspeeding. Over and above, there is another problem. So, basically if the geometry, so accounting for all these problematic issues, if we need to reduce the speed of the turbine or even compressor. So, if we need to reduce the speed of the turbine, compressor speed also will decrease, and if the compressor speed decreases, we had discussed in the previous class that in a performance map, compressor operation is restricted between two lines, one is choke line, another is surge line. Surge line means that is the zone where compressor is operating at a low speed. So, if the compressor needs to be operated at low speed, accounting for all these problematic issues of the turbine itself, then that at low speed compressor flow may be highly unstable, it will encounter surge, that is flow reversible will be there. So, considering all these things, fixed geometry turbines are not even used in turbocharger, and hence variable geometry turbines are used. So, we shall discuss this turbine, that is variable geometry turbine, the need of this in the context of turbocharger we have discussed in today's class. What is a variable geometry turbine and how does this particular turbine safeguard turbochargers, that we will discuss in the next class. With this I stop here today. Thank you very much.